Welcome to this video lecture on the ideal gas model. Now, in the previous video lecture, we talked about the incompressible substance model. That's one model we use very frequently for solids and liquids. When it comes to gases, the ideal gas model is used all the time. And you probably have some familiarity with the ideal gas model from a previous physics or especially a chemistry course. We're going to rely on it heavily in this course. And the ideal gas model is used all the time when analyzing the flow of gases. It's a pretty good model under many normal engineering circumstances, and a lot of our theoretical work is based on that ideal gas model. In fact, take a look at the picture on your screen. This is a picture of an explosion going off. You can see the explosion here, and you'll notice there's this sort of a line that looks like a hemisphere here. That's a shock wave that's formed. So there's a shock wave that's propagating out into the rest of the air. Shock waves are phenomena that show up in high-speed flows of gases, and so when there's an explosion, there's a high-speed flow of the gas rushing outward. This gives us the shock wave. Across the shock wave, the pressure changes very abruptly to a very large degree. You get a large increase in temperature, you get a large increase in density. There's a wind that follows the shock wave, so in other words, it's stagnant air out here, but behind the shock wave, there's a strong wind that follows the shock wave. So you get a big change in properties across this shock wave. And the way that we analyze shock waves relies very heavily on assuming ideal gas behavior. That's the standard way that we analyze it. It's something you would learn about in an introductory fluid mechanics course or an aerodynamics course. So I wanted to motivate the work for the ideal gas model with something where we use the ideal gas model all the time, and shock waves are one place where we do that. In fact, the flow of high-speed gases like air around high-speed aircraft or rockets and things like that, it all relies on the ideal gas model. Okay, so hopefully you're convinced it's a worthwhile model. So let's get started on it. And actually, before we talk about the ideal gas model, I just want to review the incompressible substance model. So just to kind of give you a recap of what we've been doing, we first introduced the idea of thermodynamic property tables, so we focus primarily on water, but there are thermodynamic property tables for various substances. Those property tables are the most accurate way to get property values, but they're kind of inconvenient. You have to look up values in tables, or if you're doing hand analyses where you're trying to do derivations and stuff, it's not convenient to work with tables in that manner. So often we rely on models for the way material behaves. So the incompressible substance model is one such model. In reality, the material behaves like compressed liquid behavior in those thermodynamic tables, but the incompressible substance model is a good approximation to reality for liquids and solids under normal engineering circumstances. Similarly, if you use the superheated vapor tables, for example, for modeling the vapor phase or kind of the gas phase for different substances, those are the most precise way to get properties. But the ideal gas model is a good approximation to that kind of behavior. And so in many engineering circumstances, we use the ideal gas model to just save us a little time. It's a little more convenient in certain circumstances. So again, referring to the incompressible substance model, I've just summarized a lot of the details of that model here on the page. So liquids and solids are often approximated as being incompressible. What that means is that the specific volume remains constant, and the specific internal energy is a function only of temperature. In general, it would be a function of temperature and pressure, or two properties. But here it's just a function of temperature. In the last video lecture, we talked about how the specific heat for an incompressible substance is just one value. Generally speaking, for substances, you'd have a C sub V and a C sub P, specific heat at constant volume, specific heat at constant pressure. But for an incompressible substance, the two are the same. So we just give it a C. And it's in general a function of temperature. Textbooks often have tables of specific heat values for solids and liquids. So if you look in the back of a textbook or online and such, you'll see these kinds of tables. And I show an example here. I believe I have, here we are. Here are specific heats for different substances. Now here it's listed as C sub P, but again, this is just the C. We can get rid of this sub P here. It's just the specific heat. So you can see specific heat values in kilojoules per kilogram Kelvin for different solids at different temperatures. Remember, in general, it's a function of temperature. 300 Kelvin is pretty close to, just kind of room temperature. So you see for aluminum, silver, etc., going all the way down here. Here we show the specific heat for water as a function of temperature. So you can see there is some dependence on it, right? So the specific heat does depend on temperature to some degree, but it can often be a weak dependence over a small range of temperatures. So these specific heat values are available in tables, they're available online, etc. Now, from the definitions of the specific heats for an incompressible substance, if you want to find the change in specific internal energy at two different temperatures, we would integrate the specific heat times the small change in temperature between the two temperatures of interest. If you want the specific enthalpy, that in general is a function of temperature and pressure, that's just equal to the change in the specific internal energy plus the change in pressure times the specific volume. So we derived both of those in our previous video lecture. So that's how you'd find these differences for an incompressible substance. Just keep in mind, these expressions are specifically for an incompressible substance. Now, if the specific heat doesn't vary much with temperature, and as a rule of thumb, it doesn't change a whole lot over small changes in temperatures. So, a couple of hundred, maybe a few hundred Kelvin. Depends on the substance and the range of temperatures. But just as a rule of thumb, that couple of hundred Kelvin you're not going to get large changes in specific heat. If that's the case, then the C here becomes a constant, and so it can be pulled outside the integral. And so this expression just becomes delta U is C delta T. Similarly, we could rewrite that in the specific enthalpy expression just using the C delta T, and so that's what this is right here. Now, just to kind of convince you that the specific heat doesn't change that much, here is a plot showing the specific heat for water as a function of temperature over a range of temperatures from about 5 degrees C to 95 degrees C. And you'll see that it goes from something like, well, here's 4.21 joules per kilogram Kelvin, or it's degrees C here, but 1 degree C and 1 Kelvin are the same. So that's the change, that's the specific heat in at 95 degrees C, it's 4.21, and then here at about 40 degrees C, it's about 4.18. So it does in fact change, but it's not that much. It's the change is, what is that, about 0.03 all over 4.2 roughly. That's the kind of change that you're dealing with here. The 4.2 is just kind of the average value in here. The 0.3 is the difference here. So you're getting my point here is that that's a pretty small change percentage-wise. Okay? So hopefully you're convinced that this approximation is a reasonable one when you're dealing with just small changes in temperature. Okay? All right, so that recaps the incompressible substance model. Now let's move on to the ideal gas model. So the ideal gas model, again, I'm sure have some familiarity with the ideal gas model from a previous course, and it's used to describe the behavior of real gases in the limit of zero pressure and infinite temperature. Basically, it's in the ideal gas model, the assumption is that the molecules of the gas don't interact with one another. There are no intermolecular forces. So it's really the limit of going to zero density. So the molecules are spaced far apart so that they don't really interact. But we can still use the ideal gas model under normal engineering circumstances. It still works pretty well. The two important equations of state, or an equation of state is just how you relate properties to one another. The two important equations of state for an ideal gas model are PV equals RT. You should be familiar with that. That's known as the ideal gas law. So the pressure times specific volume is the gas constant for that particular gas times the absolute temperature. And the other one is this expression here, that the specific internal energy is just a function of temperature, just like it was for an incompressible substance. And the specific enthalpy is also just a function of temperature. So that's different from what we had for the incompressible substance. So these are called equations of state. We had equations of state for the incompressible model. If I go back up here, the equations of state for the incompressible model were this one, specific volume is a constant, and this one, where the specific internal energy is just a function of temperature. So equations of state, again, just relate. They give you more information about how the properties are related to one another. So let's go back to the ideal gas model. So or ideal gas law, you're very familiar with this one. It comes in various forms, but this is the form that we'll use most frequently. Again, this is the absolute pressure. You have to use absolute pressure and absolute temperature in the ideal gas model. That's the specific volume. This is the gas constant. It's not the universal gas constant, but it's the gas constant for whatever gas you're dealing with. And the way you would find that gas constant in general is you take the universal gas constant, that's this R bar sub U. It's written here in terms of kilojoules per kilomole Kelvin. And then you divide it through by the molecular weight of whatever gas you're dealing with. So M is the molecular weight or molecular mass. So for example, for air, the molecular mass is 28.98 kilograms per kilomole. So to find the gas constant for air, what we would do is we'd take this universal gas constant divided by the molecular mass, and then we would end up with this. So the gas constant for air is 0.287 kilojoules per kilogram Kelvin. That's another number that is worth memorizing because we use it so frequently. So if you remember in the last video lecture, I said that one number worth memorizing was the specific heat ratio for air. That's that K value. That K value for air is, again, that's Cp over Cv. Just remember a value of 1.4 for air, because we use that all the time. The other thing to remember is the gas constant for air is 0.287 kilojoules per kilogram Kelvin. We use it all the time, so it's worth remembering. So I think you have some familiarity with using the ideal gas law. So that's hopefully that we don't have to review too much more about that. Now, as far as this other equation of state where the specific internal energy and specific enthalpies are functions of temperature only, what that means is that going back to the definition of the specific heats, remember C sub V is du dt at constant volume, and C sub P is dH dt constant pressure. Notice that these are partial derivatives, meaning that in general, specific heat, specific enthalpy are functions of more than just temperature. But for the ideal gas model, we're saying it's only a function of temperature, so these partial derivatives become ordinary derivatives. You can rearrange those expressions and then integrate, and so that's where these come from. So just taking this expression, making that an ordinary derivative because U is only a function of temperature, and then integrating both sides, you get that. So that expression looks very much the same as what we had for an incompressible substance. The only real difference is that this is now C sub V. Remember, for an incompressible substance, C sub V and C sub P are the same, so we just call it C. There's just one specific heat. But for an ideal gas, we do have the two, C sub V and C sub P. To get the specific enthalpy, we can just turn this partial derivative into an ordinary derivative because, again, specific enthalpy is only a function of temperature. And then rearrange it and integrate both sides. So the change in specific enthalpy is the integral of C sub P with respect to temperature. And just remember that C sub V and C sub P in general will be functions of temperature. Since the U and the H are functions of temperature in general, it means that CV and CP will be functions of temperature in general. So you need to just keep that in mind, that to be accurate when you're trying to find the change in the specific internal energy, you have to take into account how the C sub V varies with temperature. Likewise, if you're trying to find the change in the specific enthalpy, you need to see how C sub P varies with temperature to be accurate. Okay, and I'll come back to how you find the C sub V and C sub P as functions of temperature in just a moment. In fact, you know what? Let me just talk about it now. So I mentioned here C sub P, C sub V are functions of temperature. K is also a function of temperature in general. And if you want to find the dependence of these things for common gases, those are often given in tables like in the back of your textbook, or you can find them online. And I have one example here. This comes from the course textbook. So these are ideal gas specific heats in kilojoules per kilogram Kelvin. You can see we have air, nitrogen, oxygen, etc. Here we have the temperature. Remember, these things are functions of temperature. So here C sub P is a function of temperature, C sub V is a function of temperature, and the K value. So you can see the K values for air are all pretty close to 1.4. You know, certainly at room temperature, 1.4 is a good approximation. As you get to really high temperatures, like 1,000 Kelvin, it deviates. But at room temperature and close to room temperature. 1.4 is a pretty reasonable approximation for the K value. So that's how you'd get the C sub P and C sub V values in general for different substances. And again, you'd have to take in, to get an accurate calculation for changes in specific internal energy or specific enthalpy, you would have to take into account how these vary with temperature in your integral. So people have produced curve fits for C sub P as a function of temperature, same with C sub V as a function of temperature, that can be used to evaluate those integrals. I'm going to give you an easier way to do it in just a moment. Okay. In fact, you know what? Let's just talk about that. So, you know, we don't want to have to do these integrals by hand, right? It's tedious to do that by hand. So, as I mentioned, people have done curve fits for how C sub V and C sub P vary with temperature and have pre-calculated what the value should be. So what they've done is they've chosen for T1, they've chosen some reference value and then calculated what the specific internal energy and specific enthalpy should be relative to that reference value. So they've done something like this. Let me just write it down for you. And you can do the same thing for the specific enthalpy. Okay, so what they've done is they've chosen some reference value. It doesn't matter. It's an arbitrary point. We don't care about it. And the reason we don't care is because we never use the U at the temperature by itself. It's always a difference, right? We always deal with differences. So, for example, if we wanted to find the difference between the specific internal energy at T1 and T2, let me make some more space for myself. Let's say I rewrote that over here. I could do this. I'm just going to write this whole thing out. Okay, so what I'm doing is I'm just taking this where I'm using a reference value for the lower bound on my temperature, and then if I want to find U2 minus U1 here, I can express it this way, and you'll see that these two values cancel out. Similarly, those values would cancel out, and so it would just end up looking exactly the same as what I have written up here. Okay, so the choice of reference temperature doesn't matter in these tables because we're always using differences in the specific internal energy, for example. And the same idea holds true for specific enthalpy. So anyway, people have pre-calculated these integrals, okay, using that reference value, and that's what's given in this table. So this kind of yellowish table, this is the ideal gas table for air. Here's the specific enthalpy, specific internal energy. Don't worry about these quantities. We'll come back to those later in the course. They represent other properties that we'll, well, they're not properties, other quantities that we'll deal with later. Just focus on those two columns. But it's the value for specific enthalpy and specific internal energy with respect to that reference temperature. It doesn't really matter what it is, as a function of temperature. And this, the tables go further than this. I just took a snippet of it. So this is how you would find H and U, taking into account the variation of the specific heat with temperature. It's already built into this. This table did the integral for you. And so this is one for air. There are tables for other substances like carbon dioxide. By the way, these tables come from NIST data. I've talked about how our property tables actually come from NIST. So this is where this comes from. So here's a table for carbon dioxide. The one thing that you'll see a little different in the one for carbon dioxide is instead of, like here for air, it was kilojoules per kilogram. Here for carbon dioxide, it's kilojoules per kilomole. So to get that to kilojoules per kilogram, you have to divide through by the molecular mass. So what you do is you take the molecular mass of the material. So here we're dealing with carbon dioxide. So the molecular mass of carbon is about 12 kilograms per kilomole. Oxygen, the molecular mass is almost 16 kilograms per kilomole. So CO2, there's one carbon, two oxygens. So the molecular mass of CO2 is about 44 kilograms per kilomole. So to get the specific enthalpy at 220 Kelvin, we take the molar specific enthalpy, which would be 6601 kilojoules per kilomole, that's this one, and divide through by the molecular mass of 44.01 kilograms per kilomole. I've got this flipped upside down. This should be kilograms per kilomole. And then that will give you the specific enthalpy value here in terms of kilojoules per kilomole. Or, sorry, kilojoules per kilogram. And you can do the same thing for specific internal energy. Okay, so just be aware that some of the tables are in kilojoules per kilomole, so you have to kind of look closely at that. And again, this is how you would do that conversion. So there are tables that exist that already do these integrals for you. So it's easiest just to use those tables rather than doing the integral yourself. You could do it yourself, but it's tedious and you're likely to make mistakes. So just use the pre-calculated tables. Another thing that we can show, and I'm not going to go through the derivation here, but it's a handy relation, is that the specific heat at constant pressure is equal to the specific heat at constant volume plus the gas constant. So this gives us a handy way to relate C sub P and C sub V. And you can see that C sub P is always going to be larger than C sub V for an ideal gas. That's something we talked about in the previous video lecture when we introduced the idea of specific heats. I said that C sub P is greater than or equal to C sub V. It's equal if it's an incompressible substance, but for an ideal gas, C sub P is always greater than C sub V. And you can refer to my book style notes for that derivation if you're interested in that. But that's a handy one to remember. And just like when we talked about incompressible substances, we said that if you're dealing with temperature differences that aren't too large, the specific heat doesn't change very much with temperature, so we could assume it's a constant. We can do the same idea here for ideal gases. So if we're dealing with a temperature change less than a few hundred Kelvin, as long as we're far enough away from the freezing point, for example, we can say that the C sub V and C sub P are relatively constant. And when I say far above 0 degrees C, I'm referring specifically to air, which you'll see here in just a moment. If you're going to assume C sub P and C sub V are constants, it really depends on the substance you're dealing with and the particular temperature range you're dealing with. You have to look at plots like this one to just see how the heat capacity or the specific heat, that goes by both names, varies with temperature to see whether that approximation is a reasonable one. So for air here, this is the specific heat as a function of temperature for air. You can see below 0 degrees C, there's a pretty strong dependence with temperature. This, assuming that C is a constant, or C sub V and C sub P are constants in this range, probably isn't a very good assumption. But once you start getting out here, you can see these curves are pretty flat, and so over just a couple of 100 Kelvin here, you can see there is a change in the specific heat, but it's not a whole lot, right? You can see the axis here goes from 1 to 1.7. So it does change, but not a whole lot. So assuming that it's a constant over that range, it's probably not too bad. Okay, so if you assume that you're dealing with constant specific heats, then these expressions up here, you can assume the C sub V, C sub P are constants. They come outside the integral, and then the expressions look like that. And if you have that kind of behavior where the C sub V and C sub P are constants, we call that a perfect gas as opposed to an ideal gas. So it's even better than an ideal gas. It's a perfect gas because the specific heats are constant. So only if you're dealing with small ranges of temperatures can you make that assumption. You're always much better off to use these expressions and the ideal gas tables because those will be more accurate. But if you're doing some hand analyses, and again, you don't want to refer back to tables and such, then this perfect gas behavior is a pretty good model as long as you're dealing with relatively small changes in temperatures. So that's one that we'll use from time to time. But in ordinary calculations and such, you're better off using these expressions with the tables. Okay. And as I mentioned down here, specific heat values for air and other ideal gases are often given in textbook tables. I think I showed that already. And then property values for air, taking into account the temperature dependence of the specific heats, are also available in tables, which I showed already. So those were these yellow tables here, as well as this table here. Okay, so now we've covered an incompressible substance model, We've talked about property tables, that was a while back, and now we've covered the ideal gas model. So I have examples where I use the incompressible substance model and the ideal gas model in various circumstances, so you'll want to look at those example videos separately outside of this.